In today's video, we look deeper into SKALA, the unique computer that once controlled the Chernobyl reactor. But not just at the machine itself, but into how operators actually worked with it, what those controls really did, and what it meant to sit in front of the SKALA console. All this is essential for what comes next, because in our lab we are building a fully functional replica of the SKALA controls. It is the next step in our ongoing project, creating a working hardware simulator of the Chernobyl reactor control room. Let's start with one core concept. So, what do reactor operators actually do? Their main task is to watch the system and to keep all its parameters within limits and the set points, so the reactor operates safely and efficiently. An RBMK reactor is a system of thousands of dynamic elements. A human physically cannot control that much at once, so here comes the SKALA system, which provides operators with monitoring and vital information. The name SKALA as a word means a cliff, but in fact it's acronym for System of Control and Automation of Leningrad Atomic Power Plant, because back in the day it was first installed exactly there, at the first RBMK unit ever. And in simple terms, SKALA is a set of two customized industrial control computers called VNM3. The core of each machine is V3M processor, and each had 20,000 24-bit words of memory, not bytes. Well, in modern terms, one such word equals 3 bytes, and that was the smallest natural unit the system worked with. Yeah, I expect the question. No, it could not play Doom or run general-purpose software, and actually even compared to mini-computers of the same era, such as PDP-11, its memory was quite modest. But here is the trick: computing power was not the main challenge. The real task was something very different: processing and converting thousands of analog signals in real time. And for this, you still need entire racks of interface equipment that help the processor talk to countless detectors, so SKALA had them as well. The problem of SKALA, however, was that it sometimes was far too slow, because some signals were requested only periodically. A good example of this you could see in our video with the last signals of Unit 4. We translated the output into English to make it more understandable, but other than that it pretty much matches the original timing. Technically, this is the output of the DREG program. It's like a reactor's black box. But the problem is, the time printed is when the signal was processed, not when it was registered. In other words, sometimes it showed the status of equipment that basically didn't exist at that moment anymore. For normal operation, this speed was quite okay, but for such an abnormally fast unfolding event as the Chernobyl accident, that was too slow. And this left us with many blank spots about that night. We printed our simulation on a modern dot matrix printer, because the actual output of DREG was produced on a high-speed drum printer called ACPU 128. That device was far too big for our lab. Yet it was not the main output system. SKALA in its original form had no displays. It's only later, when in Chernobyl Unit 3 was added so-called DES auxiliary system, there appeared computer monitors. But the main output was always made on teletypes of the RTA-80 type. The logic behind this choice was simple: if something happens, a readable paper printout will always remain. Each of the two computers could have up to 4 teletypes, and their purpose was different. Some registered deviations in parameters, some registered malfunctions, and some were in reserve. You may remember that in 2023 I mentioned I would love to get such a teletype and eventually wire it up, but unfortunately still no success. But one day I believe that will happen. Now, to run all that you need software, and it works here quite unusually, because there is no operating system in SKALA. Instead, there is a collection of bootloading code and the sources of all main programs on a few punch tapes together called the library. The library is used only to generate executable code on magnetic tape. It takes around 1 hour, and that's why it's not done often, only if there are actual changes in the code. So where does this tape go? SKALA system had a few tape reel drives, and each had its own function, and a few were always kept in hot reserve. This library tape is always placed in drive number 1, and it acts as read-only memory. And then, when the machine starts, it boots the software from the tape, utilities and control programs. Some of them work only in memory, but some also use other drives. For example, the diagnostic program DREG I mentioned before writes everything to its own tape, which is always in the drive number 5. In case of Chernobyl Unit 4, that tape was later retrieved and became one of the primary sources during the investigation. Then there is a program called Archive Restart. Well, its purpose comes from its name. It's basically a snapshot of the all operating parameters of the SKALA system. This tape is changed every day, and it's always in the drive number 3. Drive number 6 is in reserve, and drive number 4 is a storage buffer for programs when the tapes are being prepared. When not used, it is just in hot reserve. But what is the purpose of the drive number 2? Well, it is the dedicated drive for perhaps the most important control program, called PRIZMA. The name PRIZMA stands for Program for Calculation of Power of the Apparatus. And to better explain what it exactly does, let me make a tiny but important side note. So, a nuclear reactor is not just some sort of a cylinder full of randomly positioned fuel, control and protection rods. To make it work, each element must be in its place. So, for every reactor, there is so-called a reference neutron physical calculation. That is basically a mathematical model of how the reaction should work inside, and that is what operators refer to in their work. So, this model, along with various constants, positions of control and protection rods, and other important data, is encoded on a PRIZMA magnetic tape. Now, when the reactor works, the processes inside change over time. Also, an RBMK could be partially reloaded without stopping it, or rods could be swapped for higher efficiency, because actually they burn out unevenly. So, PRIZMA program periodically accounts for the positions of control and protection rods, the actual vertical distribution of energy, pressure and temperature of coolant, temperature of reactor graphite, and much more. And then, based on all this, it corrects this neutron physical model and writes those changes onto magnetic tape. Apart from PRIZMA, there are 5 more control programs. Their names are acronyms as well, but they are pronounced as words. The first is KIKD program. It monitors the flow of coolant through the reactor's active zone, its so-called coolant consumption. Each reactor has massive circulation pumps that move the coolant, and there is a system of piping coming from each reactor channel to special collectors. On each of those pipes there is a rotameter, and KIKD program reads them once per minute. Then there is a KCTK program for control of the integrity of the reactor channels. Remember this green display we made last year? So this program interacts with detectors that watch for leaks inside the active zone. And just like KIKD, it does it once per minute. Then there is KIKD, which once per minute checks that detectors are functioning properly. And finally there is RAO, which registers emergency deviations and triggers certain alarms. Most of these programs watch for various deviations from normal operation and set points, and then advise operators on required actions. They trigger mnemonic displays and log everything on the main teletype. But how do operators actually interact with those programs? Well, like any computer, SKALA also has a keyboard and displays, but very unusual ones. Like this, it consists of 2 request devices and 6 VFD displays. Each reactor operator has their own set of these devices, and there is also a Chief Computer Operators panel where these controls are grouped together. So, using them, the operator can check that the chosen parameter doesn't go below or above the set point. They can write changes or they can request information about the status of systems or some devices. This is why it is called a request device. Each system of RBMK unit and each part of it has its own unique code. You enter it here using the 7 columns of buttons. The first one refers to the largest group of equipment, marked with Cyrillic letters K, Y, A, P, N, D, T, and M. For example, A is the reactor itself, N is pumps, D is the deaerator, and K is a reactor channel. The second is the number of the control section of the selected equipment. The third one is the type of a parameter, what exactly we need to get from that equipment. Here it is marked with Latin letters X, N, S, H, P, G, and T. For example, N is power, H is level, P is pressure, and G is consumption. Finally, the last four columns marked with digits are used either for identifying a specific part of the equipment or, in the case of reactor channels, a coordinate inside the reactor. If you look at the reactor control panel or at the mnemonic display with channels, you can see those octal notations. Those are exactly the coordinates, horizontal and vertical. Let me give you some examples. So, this code will get information about the temperature of gas in channel 4136. And this one, how much coolant is passing through it. If you enter this code, you can get the same data, but for the entire left half of the reactor. This code will print a map of the position of control and protection rods. The problem is that the number of these codes is incredibly large. It takes a lot of time to learn all that and to quickly pull the right one from memory to enter. And this is how you enter it. So let's take a random code, say K0G4136, which shows the coolant flow in channel 4136. Then we press measurement and then one of the buttons below to select how we want this information to be presented. For example, I choose PRM, that means get the value and deviation, and then I hit this switch, it's like an enter button. And on the displays will appear the code I entered and the value. On the middle one, how much this value differs from the set point, or there will be 4 zeros if no set point is defined. This is because not everything has a set point. And here also can be other numeric error messages depending on the situation. For example, pressing this button will show the minimum and maximum possible value of the requested parameter. These four buttons are very important because they are needed to check the values of warning and emergency set points. Next, we have this second keyboard, which looks a bit different. You use it to start subroutines and utilities. Each subroutine has its own code, which consists of one of these digits, then sign plus or minus, and 4 digits selected here. Utilities are triggered using these buttons, and their operation is indicated by these light bulbs. And now starts some magic, because you can actually use this to show something on this large mnemonic display of the reactor channels. There are two utilities, number 4 and number 8, for working with those displays, so we select one of them. Now, say you want the display to show you all the channels where the coolant flow is too low. To achieve this, you select M on the left keyboard, and then here you press 0 plus 0001. And then we press this button, which is basically Enter. This is the code of the subroutine for that very task. And we get something like this. There are more controls and more functions, and in reality you can make far more complex things here, but we will talk about them in the next video because it will be much better to show them in action. But for now I believe you already got some perspective on what it means to work with the SKALA system. And now I would like to show you one more component of it, which is very beautiful in operation, and it reminds me some sort of control panel from the original Star Trek. It is a status monitor called Mnemonic display of the SKALA system. So, it has these 3 large electroluminescent panels that glow a beautiful turquoise color. The left one indicates loss of power supplied to different parts of the system. For example, those circles refer to the channel mnemonic displays. The central panel is perhaps the most important, because it shows which processor is active. You may remember that SKALA is two-machine system, so on this panel they are marked as the control computer A and control computer B. When a processor is working, the frame around it glows. Then, between them, we have arrows which indicate their status. Here are ready, hold and malfunction indicators. Well, the meaning is quite straightforward here. But above there are standalone operation and paired operation, and those are quite interesting. Depending on the task SKALA performs, the operator can allocate hardware resources in different configurations. Sometimes it can be two single machines, but more often it could be 1.5 machines, which means one processor uses part of the resources of the another one. Or there could be two machines working as a pair. That will be indicated here. Next, what are those colorful blinking lights? Well, they indicate operation or malfunction of those 24 functional control groups that establish the link between processors and peripherals. Now, what if we have a malfunction of some device? Well, in this case, the operator must restrict the software's access to it so the system retains its integrity. For functional groups it's indicated here, and there are extra signals for restricted teletypes and restricted tape reel drives, because those peripherals are especially important. But malfunctions can also happen to the main programs, and this rightmost panel indicates exactly that. It says restriction of functions, and below we have the names of those main control programs I mentioned before. In addition, if there is a need to draw attention, there is a huge loudspeaker hidden here, which makes some sort of a siren-like alarm. So I hope this brief overview will come in handy, because we are building a functional replica of the operator's control of SKALA. And we started with this very mnemonic display, which I believe you would love to see in action. Then we'll add it to a replica of this control console and wire this all together to our reactor control panel. So after programming, it will become one functional complex. Updates on this project you can find on our Patreon page, and we are very thankful to everyone who supports our work. Because that helps bring the Chernobyl history back to life in a way it was never done before. And that said, stay tuned, thank you for watching, and we will see you in the next one.